Hello and welcome. Today, we are diving into a hidden science, the science that literally keeps our entire world from falling apart. It's called strength of materials. And, it's the secret reason why your chair, your house, and even the phone in your hand don't just crumble under pressure.
I mean, really think about it for a second. How does a massive bridge or a skyscraper or even an airplane wing just work? It kind of seems like magic, right? But it's pure science. So today, we're going to be engineering detectives, uncovering the clues that explain how these incredible structures defy gravity every single day.
And the key to solving this whole mystery is this field right here, strength of materials. To put it simply, it's the rulebook engineers use to figure out how things react when they get pushed, pulled, twisted, or bent. The goal? To design things that are not just strong, but safe, reliable, and totally efficient.
Okay, let's get into it. Here's our roadmap for this explainer. We're going to start with the invisible battle that's happening inside every single object. Then we'll learn the language engineers use to talk about it, explore all the different ways materials can be attacked, look at the silent threats that cause things to fail over time, and finally, see how all this knowledge lets us build our world with confidence.
All right, first up, the unseen battle within. This is where we get into the two most fundamental ideas in all of engineering.
The first one is stress. I want you to picture a rope in a tug of war. The pulling on the outside, that's the load. But stress is the invisible, internal force inside the rope's fibers, fighting like crazy to hold everything together. We measure it as the force applied spread over a certain area.
And the result of that internal fight? Well, that's strain. Strain is the physical evidence of the battle. It's how much the rope actually stretches, or how much a concrete column gets squished. It's just a simple ratio. The change in length compared to its original length.
So, to put it as simply as possible, stress is the invisible internal cause, and strain is the visible external effect. You could think of it this way. Stress is the fight happening inside, but strain is the change you can actually see and measure on the outside.
So now that we have a handle on stress and strain, how do engineers actually use them? Well, let's move on and see how this all builds into the language they use to predict a material's entire life story.
It all starts with a really simple but incredibly powerful rule called Hooke's law. This is basically the rule of bounce back. It just says that for most materials, if you pull on them a little, they'll stretch a proportional amount, and then when you let go, they'll spring right back. That E in the formula, Young's modulus, just tells us how stiff a material is. Steel, for example, has a super high E, while something like rubber has a really low one.
But, and this is a huge but, this only works up to a certain point. Every material has a limit, and that limit is known as the yield point. Once you push it past that, well, you've hit the point of no return.
And this curve right here perfectly illustrates that whole life story. In the elastic zone, everything's fine, it'll spring back. Then you hit the yield point, and that's when permanent damage starts. In the plastic zone, the material is stretching out, and it's never going back to its original shape. And finally, you reach the fracture point. Game over. The material breaks.
Of course, in the real world, things aren't just pulled in a nice, neat, straight line. Forces can attack from all sorts of different angles.
And this table lays them out really well. You've got tensile stress, which is from pulling, and compressive stress from squeezing. Shear is a sliding force. Think of scissors cutting through paper. Bending is exactly what happens to a bookshelf when you load it with way too many books. And torsion, that's a twisting force, like the one you'd find in a car's drive shaft.
Okay, so sometimes failure isn't some dramatic, sudden event. Sometimes it's a really slow, creeping process. You can think of these as the silent assassins of the engineering world.
The two main culprits here are creep and fatigue. Creep is caused by a constant load over a long time, especially when it's hot, and it makes things slowly sag. Fatigue, on the other hand, is from a repeating load. You know this one. Think of bending a paperclip back and forth. The force isn't huge, but doing it over and over and over again eventually causes it to snap. This is what engineers are fighting against in things like airplane wings and engine parts.
Okay, so we've got all this knowledge about stress, strain, breaking points, these slow killers. How do we actually use it all to build things that don't fail?
Well, the answer is actually deceptively simple. Engineers always plan for the unexpected. They never design a structure to be just strong enough. They do it on purpose. They over-engineer it, building in a calculated buffer for safety.
And just how big is that buffer? Well, it varies, but a really common number you'll see in tons of general applications is this one, 1.5.
So what does this mean? This is called the factor of safety. An FOS of 1.5, for example, means a part is designed to be 50% stronger than the absolute maximum load it should ever face. And here's the key. This isn't a guess. It's a precisely calculated shield against uncertainty, against unexpected events, and even against tiny, invisible flaws in the material itself.
And that is why all of this matters so much. This science is what lets us live in a world with towering buildings, high-speed trains, and all kinds of incredible machines. It's the foundation of confidence that lets us predict, calculate, and build a world that is, fundamentally, safe and reliable.
So I'll leave you with this final thought. Right now, as you're sitting there, your chair is in a constant, invisible battle. There are compressive forces pushing up through its legs, maybe some bending in the seat. It's a tiny engineering marvel, and it's quietly winning its battle against stress and strain, all thanks to these principles of strength of materials.